is Yizhi. Yizhi did her PhD at UIUC under the supervision of Eduardo Fratton, and then she was a postdoc at Princeton, and currently she is a MSc research scholar at Oxford. And soon she will be joining Northeastern University as an assistant professor. Yizhi has a broad range of interest, including topological phases, Maranas, fractons, entanglement, and quantum dynamics. Uh, Her talk will be on interaction-enabled fractonic higher-order topological phases. Please go ahead.
Yeah, thanks. Okay, thanks for the introduction, and thanks for the organizers for putting up this wonderful workshop. Today, I will talk about interacting-enabled fracton higher-order topological phases. And before I proceed, I would like to thank and acknowledge my collaborators on these type of topics. So the work on solvable models and couple-wide construction was completed by Taylor Hughes and Julian in UIUC and Jim B from Penn State. And the field theory aspect was developed with Fiona Bonero and also with Taylor Hughes. Okay, so before we proceed, I would like to talk a little bit about the motivation of this work. So in 2D, can everyone hear me? Yeah, good. So in two spatial dimension, one of the most prominent examples of ultra quantum matter was probably the quantum Hall effect, or the family and zoology of quantum Hall effect, where we can have an insulating bulk with a chiral charge current propagating at a boundary with a quantized Hall conductivity and thermal conductivity. And here, one question I had in mind before, and that partly motivates this work, was, can we extend such kind of quantum Hall feature in three spatial dimension? So what does it mean by extend such kind of feature in three spatial dimension? What I want to ask is it possible to construct a lattice model or whatever interacting system in three spatial dimension such that there is a chiral propagating mode, like chiral propagating charge mode or neutral mode, living at the surface or living at the boundary? So this is a bit tricky, and actually such kind of generalization was explored for decades. There have been several progress on this. First, one of the extension on quantum Hall effect into spatial dimension was known as the 3D weak Chen insulator or weak topological insulator. And the idea is just stacking 2D quantum Hall effect or stacking of 2D Chen insulator along the third direction and allow some of the tunneling or coherence between them. And hence one can expect there are a large number of chiral propagating boundaries along the surface. So this is one generalization, but this is still some type of 2D stuff because we are just stacking 2D quantum Hall layer in the extended directions. And recently, due to the explorations of some topological crystalline insulator or topological quantum material protected by spatial symmetry, one can also find that there exists a zoology of charge insulator, which has a charge gap in the bulk. And for most part of the boundary, they're also fully gapped. But along some special high symmetric point, like a special high symmetric hinge, there could be a 1D propagating chiral mode living there. So this is one generalization. But again, this is more like a trivial 2D generalization because this was first pointed out by Mike Hermley and Leon Fu. Most 3D topological crystalline insulator protected by some spatial symmetry like inversion or reflection can finally be reduced into a 2D problem because we just need to put some 2D physics on high symmetric planes or high symmetric points. Okay, so to be more precise, what I want to figure out is it possible to have something like a quantum Hall feature in three spatial dimension? And also, is it possible to have such kind of quantum Hall feature in three spatial dimension in a fracton system with subsystem symmetry? So if we look into the schedule of this workshop, I believe there will be a lot of interesting talks on fracton physics and beyond. So today I will not give any introduction or preliminary knowledge on fracton because I believe other speakers would have a more coherent and comprehensive understanding on this topic. So what I mean by fracton here is a system with subsystem symmetry or a system whose charge or quantum number is conserved on a submanifold. That's it. So now let's complete our setup. I'm looking at a 3D system, which can be built on a 3D, something like a cubic lattice. And what I want is some fractal phenomenon. So we need a subsystem symmetry. And what I'm looking at is, suppose we have an interacting fermion, which carries a U1 charge. And here, my constraint is that the charge is not just conserved globally in the 3D space. Instead, I want a special type of subsystem symmetry where the U1 charge are conserved on two intersecting planes. So in particular, the U1 charge is conserved on any XZ plane, like the purple layer I plot here, and any intersecting YZ plane, like the green one I plot here. So I have a constraint that the charge is conserved on any 2D planes along the XZ direction and the YZ direction. So this is a special, what I call the subsystem symmetry, such that charge are conserved on 2D submanifold inside a 3-dimensional space. And under this constraint, what we can expect is, because charge is conserved on these two types of planes, I don't expect there could be a charge current or current with a charge carrier that can move along the X or Y direction, because such kind of current would obviously break this charge conservation. Instead, the only charge carrier or only current carrier which can carry a U1 charge is a current propagating along the Z direction. So this is the symmetry constraint. And now let's look into the physics I'm looking for. I'm looking for a system. I don't know what are the microscopic models or what are the microscopic settings. I only know there's a system with such kind of charge conservation. And I hope I construct some microscopic model or field theory such that the charge degree of freedom is fully gapped inside the 3D box. And on most part of the boundary, they are also gappable. However, what I'm expect or what I'm anticipating for is, I expect there could be a chiral propagating charge mode along Z direction on the full hinge. This could be regarded as a generalization of the 2D quantum Hall effect. For 2D quantum Hall effect, we have a charge gap in the bulk, but at the boundary, we have a propagating charge mode on the boundary. And here, we have a special type of subsystem U1 charge, and I expect the charge degree of freedom should be fully gapped in the bulk. However, we can have a chiral current living on the hinge along the Z directions. So this is more like a dipole current if we extend our horizon on the side surface. So if I take one of the side surface, we can expect there is a charge current moving in the plus Z direction, and there's another charge current moving in the opposite direction. So this is more like a dipole current where charge and anti-charge propagate along the Z direction. Okay, so this is the setup, and we know we have a certain type of exotic symmetry called a subsystem symmetry, which is closely related to fracton, and I believe lots of other speakers would demonstrate more on this topic. And I also want to construct or realize a system which has a property such that the charge degree of freedom is fully gapped in the bulk, and there is a chiral mode living at the hinge. And how do we realize them? In general, there are two ways for me to tackle such kind of problem. And first is probably construct some solvable models which manifest the physics I want. And second, which is probably simpler, is even without knowing what type of microscopic Hamiltonian can realize such exotic physics, I can first predict or characterize a possible topological response theory that captures the silent features, including the subsystem symmetry and the chiral propagating mode living on the hinge. So I will begin with the second part, and we will go back to the first part a bit later. So how do we do that? Now we know our system has a subsystem U1 symmetry, and if we have a U1 charge conservation, we can couple them to some external electromagnetic field and see what type of electromagnetic response can we anticipate. So now we have a U1 charge conservation such that the U1 symmetry on any type of XZ direction and YZ direction has to be conserved. And that also means that if we have a microscopic fermion, the fermion can only hope, a single fermion can only hope along the Z direction. So we could have a charge current along the Z direction, and such kind of current would minimal couple with a gauge potential, AZ, which is similar to the usual AZ gauge potential in the ordinary 3D electromagnetic theory. And in the meantime, because charge are conserved on these two intersecting planes, there's no single charge current along the X or Y direction. But instead, we can anticipate that a pair of charge and anti-charge can form a bound state. So suppose this is the XY plane. We can have a charge and anti-charge forms a bound state, more like a dipole with plus charge here and minus charge here. And we can let them hope along the perpendicular direction, along the Y direction. So such kind of coupling is more like a dipole current, where a dipole of X can move along Y, or this can also be regarded as a dipole of Y moving along X. And this dipole current would minimal couple with a rank 2 gauge potential. I call them AXY because the gauge potential should live at the center of the XY plaqué. So these are the only two type of gauge potential term we can write down. And one of them coupled with the charge current along Z direction, the other coupled with the dipole current on XY plane. And we also have a time component, which minimal coupled with the charge density. That's it. And if we have a couple them to an external electromagnetic field, or say prop field, we can first figure out what are the possible gauge invariant operators. There are two types of new gauge invariant operators. One is something like EXY, which involves a time component or time dependence of a spatial component. This is what I will call a higher rank electric field. And we also have something like a higher rank magnetic flux operator, which could minimal couple with the charge density. That's it. So now after we set up the external electromagnetic field, what we want to ask is, suppose I have a system with such kind of exotic subsystem U1 symmetry, and we couple them with the electromagnetic field. If such kind of system has an insulating bulk with a chiral current propagating along these two hinge along the plus Z direction, and the other chiral current on the other two off-diagonal hinge going along the minus Z direction. If such kind of system exists, what type of topological response can we write down that exactly captures this feature? So here it's a bit tricky because at this stage, I still don't have any microscopic Hamiltonian or microscopic settings for this system. I just assume this exists, and I want to see what type of electromagnetic response can we expect. So now what we can do is have some guessing. Suppose we have such kind of system exist and we want to write down a topological response that captured the feature. Then such kind of response should at least obey the following 4 rules. First, because it's an electromagnetic response, it at least had to be gauge invariant in the bulk. And second, because we know there is a chiral propagating current along the z direction living on the hinge, such response theory should exactly predict the current anomaly living on the hinge along the z direction. And it should also capture all of the silent features we can expect. And what are the silent features? This is something I want to talk about in the next few minutes. And finally, there are a lot of electromagnetic response one can write down. For example, as we just defined what are the electric field and what are the magnetic flux operator, you can just write down a Maxwell theory for that. But what I want is more exotic. We hope that the response coefficient should be quantized, or at least to be discrete under a certain constraint, and should be robust to whatever perturbations. There is a question.
Yes, there is a question by Nati. Could you?
Yeah, I'm puzzled by some of the things here. When you say electromagnetic response, do you mean do you refer by EM to the gauge field on the previous slide?
Yes.
Okay, so it's not electromagnetism.
What I mean
When
by
you wrote EM, it's not that you couple that to another U1 gauge field, but you refer to this gauge field.
Yes, and these are the external probe field I want to couple to the electron.
Okay, so now that I understand the first line, I have questions about the others. Could you go back to the next slide where I had the question?
Yes.
You say that there's an anomaly. An anomaly in what?
The current anomaly of the U1.
But when you say there's an anomaly, there's always an anomaly in something. There's a situation without the anomaly, and it is to be contrasted with the situation with the anomaly.
So what I mean by anomaly is if the full system is definitely anomaly free, but if we only take part of the system, like if I only focus on the part of the hinge here and ignoring the rest of physics, the anomaly is just a charge anomaly where the charge is not conserved.
I don't understand what's anomalous about it. Is there a global symmetry that has an anomaly? Or what is the thing that is anomalous?
So the anomaly is if we insert if I only look at this hinge, if I insert a subsystem U1 flux, you will find that the charge number would be shifted by an integer.
Integer in what units? You
So
didn't
the
tell us
U1
how you quantize things, so I don't know what an integer means. I have a related question to number 4 here. When you say quantize coefficients, it's quantized in some units. Is it quantized in kilograms, in pounds, in Fahrenheit?
It's quantized in the elementary charge over E squared over H bar.
But you didn't tell us how you don't normalize the charge.
Correct.
So
Especially
my
here.
normalization of the charge could differ from yours by 1.3. Okay, well, go on. I don't want to derail the talk.
Okay, so now let's see what are the silent features we can anticipate. So here I don't know what are the microscopic detail of the physical system which can realize them at this point. And all I know is suppose we have a symmetry and suppose that there is a chiral current only propagating along the z direction. Then what type of features can we expect if we only know about this? Well, first, since we previously defined something like a high rank electric field. So suppose we put a high rank electric field by having a spatial gradient gauge potential in space along both x and y direction. Then there is a lifting chemical potential difference between one of the hinge with the other 3. And what one can expect is, since we have a chiral chiral fermion living here, there should be a charge current response to the electromagnetic field. So this means once we turn on EXY, we can expect there is a charge current going along the Z direction. This is more like the Hall current in analogy to the 2D quantum Hall effect, where we have an electric field in one direction, then we should have a charge current going along the transverse direction. Here, what we have is we have a high rank electric field EXY, and the response is along the Z direction. And second is more similar to the Laughlin argument. Once we know there is a chiral current living on the hinge. And now I make the Z direction periodic and inserting a 2π flux, which would eventually shift the momentum of Kz by a 2π divided by spatial length L. And since we have a chiral fermion here, and we have another chiral fermion living on the other direction here, inserting a flux would finally end up with that we will lost a charge here, and I have a charge here, and the same for the other boundary, for the other two hinge. So this process is more like a dipole pumping term, where after I insert a 2π flux phi z along the Z direction, we will have a pair of charge E and minus E pump to the other two hinge in a parallel direction. So charge pumping finally engenders dipole pumping between the two parallel hinges. And this actually means that if I put a constant gauge potential AZ, we can expect there is a quadrupole moment generated by that. Or at a time, if I change AZ or inserting a global flux, which is more like creating a electric field in the Z direction, I can expect there is a dipole current where a pair of charge E and minus E spatially separate along X direction can be pumped along the Y direction between. And now I have another assumption without looking into the microscopic detail. I assume that all of the excitation, either gapped or gapless or whatever, does not have any symmetry fractionalization. So all of the excitation should carry an integer charge. And hence I can expect that the dipole charge E and minus E here that can be pumped from the two hinge to the other two hinge should also be an integer. And this probably would impose a condition for the coefficient. Okay, so that's all of the silent feature we can expect, and all of the silent features we anticipate here is just by the fact that we have a chiral fermion living on the hinge. So first, we know that if we have a chiral fermion living on the hinge, we should have something like the Hall effect in analogy to the 2D quantum Hall effect, where whenever we have an electromagnetic field EXY, it should induce a charge current along Z direction. So by some emotional guesswork, I can write down this term, which exactly characterizes this Hall response feature. And second, we know that once we insert a 2π flux along the Z direction, one can expect there is a dipole pumping process. So there should be some term that look like this. And finally, we know that there should be a chiral fermion living on the hinge. And we also expect that the theory at least need to be gauge invariant in the bulk. So after all of these constraints, it seems that the only term one can guess without deriving the microscopic physics is this one. This term turns out to be gauge invariant in the bulk. It can give rise to all of the linear response theory we expect here. And if we put them on an open boundary condition, one can expect that on the hinge, there turn out to be a chiral propagating mode on the four hinge propagating along the Z direction. So that's it. So now,
I'm sorry, but I have to ask the same question again. Could you go back What sets the normalization here? Why is it 1/4 pi and not 1/15 pi?
Because I assume that the charge E, that minimal couple with the A naught, is just a unit one.
But how do you know, how do you quantize the charge? You have to say something about what kind of twisted boundary conditions are allowed.
Honestly, I never go into detail. I just assume if we have a charge which is already quantized, then what are the possible electromagnetic response I can expect?
Having quantized charge, usually the argument goes that if you have quantized charge, then the magnetic field has a certain quantization. And then in the background of this magnetic field, you would like the action to be gauge invariant. But I don't see how you could do it here. Because I don't know, you haven't told us how the magnetic field, the fluxes of the magnetic field and these E's are quantized. What kind of fluxes are allowed? All these questions I'm asking are really the same question. I think actually they're quite significant because what you did was to write the local properties of these gauge fields. That's what appears below. But you have to say, is alpha identified with alpha plus 2 pi or 15 pi or in what unit? And then you have to check what the allowed fluxes are. And I don't think it's that easy here.
I see.
But it could be done, but I don't
I
think
see.
you've done it.
I see. So here, actually, the charge level quantization is the most important thing.
Under there's assumption that the U1 is a compact, not just a R, but really U1. So there's assumption of compactness here.
Yes, Shogun, you're completely right. That's its assumption number one. But after you've assumed that, a lot more work is still needed to determine the normalization. So imagine this is being a Chern-Simons term. There's a big difference between 1/4 pi and 1/2 pi. One of them depends on spin structure and the other does not. So even in the case where it's an ordinary gauge field, there's something to be said about the normalization. But this gauge field is not a standard gauge field. So I think there's something here that needs to be addressed.
I see. Okay.
Can we ask the question from here? Hi, this is Shuhan.
Yeah.
So I have a question about the comparison between this Lagrangian and the ordinary Chern-Simons theory.
Yeah.
Yeah, so I think there's one qualitative difference. I wonder if you can comment on that. So for the ordinary Chern-Simons ADA is not the total derivative term.
Exactly, but this one is
The total derivative term. So I wonder if, so you drew a lot of analogy with the ordinary 2D quantum hole. So I wonder if you can comment on this qualitative difference between the two cases. Thank you.
Yeah, actually, this is an excellent question. So different from the usual Chern-Simons term, which is not just a purely boundary term. This term is a purely boundary term, which does not change the equation of motion inside the bulk unless you have something like a monopole. So this term is, well, this analogy may not be totally correct, but I feel this term is more like the theta E dot B terms in a 3D, three spatial dimension topological insulators, where you do have some, without inserting monopole, actually, it does not change the equation of motion or any underlying physics in the bulk, and it does not change any, but it has some impact on the boundary. And that is the same because for 2D Chern-Simons theory, if we extend to some fractional quantum Hall effect or even non-abelian fractional quantum Hall effect, the Chern-Simons term where the capital A should be replaced by little a, which is the emergent hydrodynamic current, would finally end up with quantization and hence predict the ground state degeneracy and a non-commutative algebra there. But here, so suppose, although I don't know what would be the quantization, suppose we have something, we have another more exotic coefficient here, such kind of term would not change any bulk properties like the ground state degeneracy or something like that. Nonetheless, actually, there was a study, there was a proposal on because such kind of gauge structure was widely studied by other people. And I think this gauge structure was first proposed by Kevin Slingoshich and their group. And they actually proposed something like a BF term where the coupling are slightly different. And for that BF term, that is more like the 2D Chern-Simons term, but for a high rank gauge theory, where it has impact in bulk. First, it will change the ground state degeneracy. And that BF term also suggests that high rank gauge flux of 1U1 gauge field would finally trap the charge of the other charge from the other U1 sector.
Right, but the BF term is not chiral in any sense, right?
Correct. So their BF term does not impose, does not give any chiral boundary, and that BF term is a purely bulk term which changed the equation of motion and also changed something like the Fracton's braiding statistics inside the bulk.
Okay, thank you.
Tara?
There are a few other questions on the Zoom. Please go ahead.
Yeah, so ordinary quantum Hall, generally it's hard to write down Hamiltonian, which is commuting projector. At least I know there have been recent progress by, for example, by Shogang and collaborators. But in this case, do you again expect similar difficulties, or can you find commuting projector Hamiltonians?
Yeah, correct. So first, in 2D chiral state and a non-chiral state, without a Lagrangian subgroup cannot be characterized by commuting projectors. And for 3 spatial dimension, I don't see, at least from my side, I don't know a no-go theory in here, but we face the same difficulty that if you just begin with commuting projector, it's hard to get a chiral state. And the second, here later I will talk about a few microscopic construction. What I mean by microscopic construction is not commuting projectors where both the ground state and highly excited state is solvable. It's more like a couple wire construction where the low energy physics or low energy excitation is known, but the high energy physics is ignored. And honestly, as I will mention in just a moment, even for a couple wire construction, I don't find a clear or neat way to get a chiral hinge mode, but I find something like a helical hinge mode, which can be protected by additional symmetry in addition to the subsystem U1 symmetry.
Thanks.
Nati, do you have another question, or should we
Yeah.
go ahead?
It's both another and it's the same point. This term that you wrote is a purely surface term. There's nothing.
Yes, true. It's a purely surface term.
Yeah. So then I really don't know. So then the whole set of questions that I asked before become more important, because normally the way you quantize the coefficient of the Chern-Simons term is to study it on the closed manifold, and you make sure that it makes sense. So this thing on closed manifold gives you nothing because it has only a surface term. Which really underscores the fact that it's not clear what it means to quantize the coefficient. And it's not enough to say that the U1 is compact versus non-compact, because this thing has nothing in the bulk. So in other words, if these A's are classical fields, this is not an SPT. It's not an SPT in the bulk because this term is really a boundary term written in a more complicated.
True, but actually for SPT phase, for symmetry protected topological phases, their topological response could be a could be a boundary term like the theta E dot B term.
Okay, so let's discuss that. So when you have E dot B in the bulk, it's very important that it's not a total derivative on closed manifolds. If you do not include the quantized fluxes, then so the story really splits. One, you say the gauge group is R, as Shaugan said. The gauge group is R, the coefficient is not quantized. And then there's nothing in the bulk because it's a total derivative. The other route you could take is that the gauge group is U1, then you have to study the other fluxes, and then the coefficient is quantized. Now, in your case, you have neither, because this is just a total derivative period. So that's why I don't see why it gives you that. And this is also related to the question that I asked about an anomaly in what. Since this term is not like an SPT, this term is nothing in the bulk, I don't see in what sense you have an anomaly on the boundary. And I'm really sorry for sounding like a broken record.
Okay, so first talk about the coefficient quantization. So go back into the quantum Hall effect. Usually when we talk about Chen-Simons term has level quantization, it's because that we know gauge group is compact and put them on the torus by inserting a monopole, and we want to see the compactification, and this would give you a constraint on the coefficient you can put in front of the Chen-Simons term. And there the gauge potential in the Chen-Simons term is more like a emergent gauge field, or it's more like the gauge current for the quasi-particles. And there is another more rough and condensed matter perspective of level quantization for integer quantum Hall effect or for Chen insulator, which does not have any ground state degeneracy. And there the coefficient quantization first, the E there is what we usually, your A there is what we usually write the capital A. It's the external electromagnetic field as a prop to the electrons. And there, how we know that it had to be an integer is based on the fact that once you insert the flux, the bulk degree of freedom is fully gapped without any ground state degeneracy, so it's unique. And the only thing you can change is left chiral fermion and right chiral fermion can pump one charge to the other. And if we know ground state and low energy excitation really don't have any fractionalization, then the excitation are just one charge. So you can only pump one charge at the left edge to one charge at the other edge. And hence they assume that, hence they reach out to the conclusion that such kind of charge pumping would impose a constraint that the whole conductivity for only for integer quantum Hall effect or integer Chen insulator have to be an integer. And the second question, which honestly I still don't know how to answer, is how to set the unit for the charge here. Okay, let's see the time. Okay, so now let's go on. So at this stage, we haven't reached out to anything because we just assume such kind of thing can exist or similar thing can exist. And we want to see if it exists and if there is something like electromagnetic response which characterize these features. So to go down to earth, what we want to ask is, can we have some microscopic model? It doesn't have to be exactly solvable model like commuting projector, because Taran already pointed out that for chiral state, a large number of non-chiral state commuting projector cannot realize them. Can we have some microscopic constructions that eventually realize such kind of state with subsystem symmetry and finally end up with a chiral fermion living under the hinge? So the simple microscopic construction I will adopt is just a couple wide construction, which turn out to be a popular tool to construct gapped topological phases from lower dimension to higher dimensions. So the setting is pretty simple, especially if you already know what you want at the boundary. Like if we want to construct a 2D Chen insulator or 2D integer quantum Hall effect, which contains a chiral fermion on one left boundary, another chiral fermion on the other boundary, what we can do is we can begin with a Latinger liquid, which can be decomposed into a left moving mode and a right moving mode. And we align these Latinger liquid or 1D ones and try to couple them one with the other between the wires, such that the left moving mode from the first wire and the right moving mode from the second wire would be gap out through a tunneling between them. And finally, all of the bulk degree of freedom are fully gapped. And the leftover mode is the left fermion on one of the boundary and the right fermion on the other boundary. And here, this is probably what we want because we already know what we expect from the hinge. It should be something like a chiral fermion or similar to that. And we want everything else to be fully gapped. So the setting I will adapt is I will use the couple wire construction and have a fermion wire along each z direction. So this is the projected plane where this is the z direction into the sheet. And each row or each wire that is oriented along z direction contain two sets of helical fermions. So each wire have two fermions, and we have two chiral fermion moving along z and two chiral fermion moving along minus z. And we put them as a square lattice if we look into the projected xy plane. And the elementary building block, which we will couple, is a 2 along the z direction. So if we look into the projected xy plane, it's a plaqué, where we have 4 chiral fermion, 2 from the z and the other 2 from the minus z, coming from 4 different wires. We want to couple them together. These are the elementary building block I would deal with, and I only consider the coupling between them. This is not essential, and in real quantum materials, obviously different building blocks should have interaction internally, but this just turned out to be the simplest case we can deal with from the couple wire construction, because this will finally end up with some zero correlation length limit wave function. And finally, what we want to do is we want to somehow couple them and finally gap them out. So all of the bulk degree of freedom that is composed of lots of building blocks are gap out. And on the smooth boundary on each side or each wire, we will have a leftover of a plus z and a minus z chiral fermion, but they're inside the same wire, so we can just turn on intra-wire coupling to gap them out. And the only tricky thing came from something along the hinge, where we will have 2 propagating mode going along z and 1 chiral propagating mode going along minus z. So then if we turn on intra-wire coupling, there should be still a chiral fermion left over here. So that's it. And what we'll see is first, is it possible to realize it via a simple wire construction, or if not, then can we realize some similar phenomena via the similar wire construction? Okay, the tricky thing came from the couple wire construction is widely explored, and the most fractional quantum Hall effect or non-abelian fractional quantum Hall effect can be realized by couple wire construction. But the tricky thing here is what we have a subsystem U1 symmetry, which requires that the XZ plane, which is this plane projected into this paper, the charge have to be conserved. And we also have a YZ plane. So it's a layer projected into the Z direction. The U1 charge have to be conserved. And this is makes the interaction or tunneling we can turn on within the building block highly restricted. Because once we know that the charge along XZ
I have a
plane.
question here. When you say U1, do you have 2 separate U1 or same U1?
Okay, so when I say U1 separate U1, you mean this one as a whole?
So in the XZ plane and the YZ plane, do you have a separate U1? So that they are totally different charge. Do you mean that?
Yes.
Okay.
So this is a U1, and the other layer is another separate U1, and the same in the intersecting layer, it's another independent U1 charge.
So all independent U1 charge.
Yeah.
And then, but each wire may carry a U1. So maybe this U1 in the YZ plane or XZ plane would be combination with those U1 charge on each wire.
You mean I have two helical mode inside of the same unit or inside the same while.
U1, the YZ plane and the XZ plane, and whether this U1 have some relation.
Okay, you mean different U1 from intersecting layer, do they have a relation?
No, relation to the U1 on the wire. So wire would have a U1 charge.
Mm-hmm.
You know, each wire I imagine have a U1 because you're seeing the chiral fermion.
Mm-hmm.
And but then, so the U1 on the wire and the U1 on the YZ plane, for example, are they related, and how are they related? Or maybe
Yes.
you are going to discuss it. Okay.
Yes, they are related. And then it's highly restricted because if we cannot add any tunneling between two counter-propagating mode along this direction, this will break charge conservation on this layer and the other layer as well. And I cannot let them tunnel along this direction as well. At least a single fermion tunnel here is not allowed because again, I'm breaking charge conservation on this layer and this layer. And it seems that the coupling, which seems to be allowed, is more like a ring exchange coupling, where I have to tunnel two charge together to the other two. This is one type of possible term that can respect the subsystem U1 symmetry side bulk. Or if we be more precise, let's just take out one building block or one unit, because other units are just a replica of this unit. We have a 4 chiral boson field, and we have actually 4 independent U1 symmetries. The U1 symmetry on this layer, another U1 symmetry on this layer, U1 symmetry on this layer, and U1 symmetry on this layer. There are two of them. Their combination actually becomes something like the global U1. So we have 4 U1 symmetry here in each building block, and the 4 chiral boson field actually carries 2 different U1 symmetry among the 4. And if we want to respect all of the U1 symmetry, subsystem U1 symmetry we define here, what we can see is one term we can add is this one, which can gap out some of the degree of freedom. However, in each unit, we have 2 pair of helical mode. So it's more like a 2 gapless branch. And if we just have a single cosine term, that is the only symmetry allowed term, it can only gap out one branch, but leaving the other branch still being gapless. Or an alternative way to see that this is not gappable under the symmetry constraint is that here we have a 2 pair of helical fermions. So we can just write them in terms of the 1D helical fermion propagating along the z direction. And forget about any symmetry, one can recognize that there are 4 independent mass. Here mass, what I mean by is the non-interacting mass or fermion bilinear mass, which tunnel between two fermions. We can write down, there are only 4, which somehow forms something like O4 vectors. But none of them are symmetry allowed. That means we cannot turn on any fermion bilinear mass to gap out them. But nonetheless, we can still imagine there are some dynamical mass generation such that the interaction finally engender a strongly fluctuating mass. It's more like a O4 vector field which fluctuate in space-time, but nonetheless, this dynamical mass generation can probably gap out part of the degree of freedom. And this was actually, the answer was pretty clear and widely studied in the 2D SPD boundary or 1D physics. So what we'll find is that if we couple all of the possible dynamical mass in terms of the 4 independent mass which forms an O4 vector, it finally engenders a 1-dimensional O4 level 1 with Witten term, where such kind of theory turn out to be gapless, no matter what type of interaction you can add on. And such kind of O4 level 1 with Witten term actually contains a mixed anomaly, because as long as I insert a 2-pi flux to one of the U1, say the U1 symmetry on this plane, because we have chiral fermion, and here we will have a plus E charge and minus E charge. So after flux insertion for one of the subsystem symmetry, we can see that the U1 charge on a perpendicular intersecting plane would be changed by 1. So there is a mixing anomaly such that once I inserting a U1 flux of UXZ, it will change the charge on the other intersecting direction. And that actually means that such kind of building block cannot be fully gapped. The charge degree of the fermion charge can be fully gapped out, but there's still a neutral gapless mode. So now let's be less ambitious. So even we cannot use any microscopic couple wire construction to characterize or realize a chiral moving node with a subsystem symmetry. Can I have a system which contains a helical mode living on the hinge that is protected by both subsystem symmetry and an additional global Z2 symmetry? So the setting is from the previous discussion, we will see that once we couple them in a subsystem symmetric way, there's still one gapless branch in each tube of the couple wire unit. Then let's consider 2 copies of the previous system with the opposite chirality. And these 2 copies are identical up to the fact that they carry opposite chirality, and they also carry the same subsystem U1 charge and live in the same cubic lattice. And the only difference is that the first copy we previously worked on, which is denoted as the red part, carries the subsystem U1 symmetry, and it also carries an additional global Z2 symmetry. And the second additional copy, denoted as the blue one, with opposite chirality, has the same subsystem U1 symmetry, but it is charge neutral under the global Z2. Then the question is whether we can fully gap out the system and leave it with a helical mode, with one propagating mode that carries a Z2 charge and the other propagating mode that carries a neutral Z2 charge. And in the meantime, they also have subsystem U1 symmetry. And this becomes a bit more easier, because what we need to do is we just need to couple the unit in a subsystem U1 symmetric way and make sure it preserves the global Z2 symmetry. So apart from the previous term, we can add 2 additional terms which gap out all of the branch. And finally, we end up with a insulating system where the charge degree of freedom are fully gapped in the bulk in the presence of a subsystem symmetry. But at the hinge, there turn out to be a counter-propagating mode which carries the same subsystem U1 charge, but a different global Z2 charge. And if we take out part of the boundary, like if I just take out a quadrant and move out a boundary, such kind of boundary is anomalous in the sense that we have a left moving mode which carries a subsystem U1 charge and a right moving mode which carries a subsystem U1 charge in addition to a global charge. So if we insert a subsystem U1 flux, we will see that the U1 charge is not changed because we have counter-propagating mode, but such kind of flux insertion would finally end up with creating changing the Z2 quantum number on this boundary. And such kind of cover cannot be realized in a pure 2D system. So this is the setting. Unfortunately, we still don't have a simple fixed point wave function or couple Y construction, which eventually end up with a chiral moving mode, but we finally figure out there is a counter moving mode which can be protected by additional global Z2 symmetry. And if we want to get an insulator, or we want to get any gapped bulk with a chiral mode, another construction we can begin with is a 3D topological superconductor, which doesn't carry U1 symmetry, but it carries a fermion parity symmetry. And we assume that the topological superconductor also have some Fracton features such that apart from the global fermion parity conservation, it also has an exotic subsystem fermion parity conservation, such that on any XZ or YZ plane, the fermion parity have to be conserved. And that also means that if we want fermion tunneling between sites, we cannot have a single fermion tunnel between X and Y directions, but we can only have fermion pair tunneling between them. And we can used a similar wild construction to figure out that there is a 3D topological superconductor with subsystem Z2 symmetry, such that it finally end up with an insulating bulk and end up with an insulating smooth boundary at the side surface. But at the hinge, it carries 4 copies of the chiral-Majorana mode with a central charge of 2. And although it carries a central charge of 2, it doesn't mean such kind of subsystem symmetric topological superconductor has a Z classification. Instead, it has a Z2 classification, because one can prove that if we have 2 copies of the system, then the central charge of 4 or 8 chiral-Majorana fermion living on the hinge can be realized in a pure 2-dimensional system with the same subsystem symmetry. In 2D, it's more, because this is the YZ plane. The symmetry action on the surface is more like a subsystem symmetry, that all of the fermion parity charge is conserved on all of the Y along the Y wiles. One can realize a pure 2D lattice model with fermion parity conserved on along the Y direction, such that it has a chiral-Majorana mode with central charge C equal 4 in pure 2D. So is there any question up to this point? Okay, if not, I'm running out of time, but next slide is just my conclusion and generalization. So there are a lot of opening questions or generalization for such kind of couple wire constructions to realize exotic fracton system with subsystem symmetry. So here we only consider integer Latinger liquid, but in principle, we can just adapt what K and T did for fractional quantum Hall effect via couple Y construction. If we choose to put some fractional Ys, like the age of fractional quantum Hall state in our Y construction, in principle, one can get a family of fractional state with subsystem symmetry and with long-range entanglement, such that the bulk degree of freedom is fully gapped, but ground state degeneracy is sub-extensive, which is pretty similar to lots of fracton phase of matter or fracton stabilizer code. And at the boundary, the smooth part of the side surface is gapped, but finally, there are some leftovers of the hinge modes, which are chiral helical, and in the meantime, they carry a fractional portion of the charge. And there are also other interesting trends on this couple Y constructions to fracton phase of matter, like the Yale group and Iowa State group together with Dominic Williamson figure out that one can use a couple Y or couple layer construction to get a subsystem symmetric, they call subsystem symmetric quantum Hall state in 3D, such that the bulk degree of freedom is fully gapped, but the full boundary on the side surface are gapless and dispersive. So now let's end up with the outlook part of this talk. So here from the couple Y construction, we still left over with lots of opening questions or some issue to be done. We can only construct a few examples of the non-trivial phases which contain subsystem symmetry. And it is not clear how to get a systematic protocol like the KNT work. And finally end up with a zoology of interesting fracton phases with gapless boundary. And in addition, in the couple Y construction, we can get some insulating bulk with chiral helical boundaries. And in principle, we can also couple them in a trivial way, which finally end up with a subsystem symmetric mod insulator where everything is trivial. And the question is there any phase transition? Does the phase transition or continued phase transition exist between these subsystem symmetric phases with different boundaries, and if they exist, how can we characterize them? And finally, at the end, I introduce a little bit about microscopic wire construction for a Z2 subsystem symmetric topological superconductor that contains a chiral-Majorana mode living on the hinge. And while we have a microscopic construction, the field theory description for this subsystem Z2 symmetric superconductor with a chiral-Majorana is still unknown. And we don't have an idea on how to deal with them, because in 2D topological superconductor, a simple field theory, or just not a field theory, just a linear response theory to characterize them is just a couple of them with the background V event, and we can expect there is a gravitational gravitational anomaly living on the boundary. But here the problem is even we couple them with the via-band degree of freedom and see whether there are some gravitational anomaly or any coupling like that. Such kind of theory does not fully characterize the fact that the system is Z2 subsystem symmetric or the fermion parity is conserved on intersecting 2D plane. So this is another opening questions which still to be done and we are still calling for answers. Okay, and thanks everyone. Now I can take questions.
Let's thank you. We have already thanked Yizhi for the talk. If there are any questions, are there any further questions on Zoom? Yeah.
Hi, thanks for a nice talk. So, in the talk, you talk about open up like boundaries on. You open up the hinge. So you put it on like you open up both x and y boundaries, and then you can get these hinges. Can you say something about what happens if you open up the z direction, and then you don't open up like x and y? Do you get something?
I see. So if I just make a spatial cut along the z direction and the surface is something like the xy plane.
Right. That's right.
Actually, there is still a gaplistic. There is still a gaplistic row of freedom living on the xy boundary, and a simple reason for that, without looking into the microscopic, is once you have chiral moving mode, they have to flow back somewhere else. So they can flow like if you want a more symmetric construction, it will flow into the center like this. And what type of current flow pattern is possible in this case where we have helical modes, or in the Majorana case where we have 4 chiral Majorana modes? That usually depend on the microscopic constructions, like the microscopic interaction you add between different islands, but there have to be a gapless mode on the top boundary on XY plane and on the bottom boundary on the XY plane.
I see. So they're not restricted to propagate on edges. They can like propagate on the bulk of the surface. Is that right?
True. So they are not restricted to propagating along this edge. Instead, they can like a symmetrical way to construct the model is propagating along the diagonal and off diagonal lines on the XY surface.
I see. Can you see this from the effective response theory?
Yeah. So this is more like U1 with a global Z2. Because for just a single U1 chiral, I don't know whether there is a simple couple Y construction. But if you just look at the field theory and assume that you have an open boundary terminate at Z equals 0, you'll see that there is the bulk. The surface term is not, that response term is not gauge invariant on the boundary. So you have to have some gapless degree of freedom to cancel that.
I see. Thanks a lot.
Okay, if there are no further questions, let's thank Yizhi again for the nice talk.